with whatever period that you need to do here. And then you do a set input delay. For example, this from here, this is a row in. So you define a virtual clock here, right? So you say instrument dash clock, which is virtual clock, and then max delay. So whatever delay, maximum delay, meaning 2.7 get ports for this particular port to here to be. So you can put a maximum string on it, meaning that it cannot exceed 2.7 delay from your input to this pin, to the D input of the flops. Okay, so that's your input delay using virtual clock. Likewise, you look at the register out, same thing. So you create a virtual clock called virtual clock CFG on this external. Okay, remember, this is come from you don't see this at all. This is here to kind of represent for you kind of understand what's happening. But as far as your block, you only see the output pin. You don't see any of this. So you have to define a virtual clock. And so for this example, the period is 8. So you have to know the budget. So in your design, the designer would know what budget timing you need here. So you would know how to constrain this. Okay. So for this output, we would do a set output delay. That's clock, this virtual clock, and then again that's MAC, whichever the constraint you want to put here, and then get ports state O. So that is the way that virtual clock being used. Okay, so unlike your real clock, right? Your real clock, which is rest to reg internal, that you know for real. So virtual clock has no pin, right? It has no skew either, right? Your real clock has clock port associated with it. It has actual latency, has skew, has jitter, has propagation delay. So unlike virtual clock, you don't have any of that. Okay, does that make sense? Any questions or comments? So the key takeaway is virtual clock is something you design and create to constrain the input delay, to constrain the input and output, which way you set input delay, max delay on those input path and output path. Okay, without virtual clock, you don't have a reference point to constrain these guys at all, to constrain the register out or inter-reg. Okay, so if you open up the SDC file, the time constraint file, you'll see set input delay, set output delay, and then associated with some virtual clock. Okay, in the lab, you should see that also. If you write the SDC constraint, you should see we have virtual clock in our lab in our design, in the lab design. Okay, no questions. I'm gonna move on to the next slide. So next one, I think I mentioned generate clocks a few times in the previous lesson. So I added a slide here to go a little bit more details in generated clock, so you kind of understand what it is whenever you hear the term. So generated clock basically is derived from a master clock. Okay, the master clock is basically your normal clock, your clock that is associated with the clock port. So when you define a clock in the design, that's your master clock. Okay, and so the generated clock is derived from that clock, and it is a multiple division of a master clock. So it's always going to be in phase. What I mean in phase is here. See, it's in phase, rise. So that's called in phase. Okay. So here, take a look at this circuit. So let's say you define master clock here on this clock out, clock P. So you would define create clock last name, give a name period, and get pinned. So this is your real clock and a master clock. Remember the virtual clock, you won't have any get pin. No pin associated with the clock. It's a virtual clock, but this is the real clock. Okay. In this case, from the concept of generator clock, this is a master clock. Okay. So it's driving a flip-flop, right? And then the QN loop back into the input. and then it's driven by the same clock. So you look at the signal, right? So when it's active high, it'll latch it or change. So that way you get basically a divided by 2 clock. You put another flop and become by 4. So that's how easy way to create general clock. Okay, and so on. And you can see this is general clock. So general clock, so you define a general clock here. So this is divided by 2, you can find here. So you create general clock, that's name, whatever name you want to give it. The source is going to be this pin right here. Okay, clock out, and that's divided by 2. Okay, and then get pin, you have Q. Okay, so you see it, in the create generator clock, you have to have a source, which is the master, and then the multiplier, division by 2, divider, and then the pins still have a pin associated with it. So I recall in our lab we also have a generator clock, so you can look at the SDC file, or you can, you don't know what SDC file is, you can do a write underscore SDC, or you can look under, I believe under data directory, there should be a Leon.SDC file. You can open it up. You can see a generate clock definition there. Okay, so basically this is a waveform of this of this diagram showing you the relationship between the generate clock versus the master clock. Okay, so this is divided by 2. So you can have another flop divided by 4 and so on. Okay. So hopefully now you when you hear the term generator clock and virtual clock, you kind of know what it means. Okay. So the advantage of having the generator clock is that there's no new domain clock. You just use the existing clock and create a new clock divided by 2 clock. So it simplifies things in terms of building clock trees and also in your design much easier. So you'll see most of the design, you'll see a generic clock and virtual clock. So I felt that's important, so I added these 2 slides as part of this today lesson. Okay, any questions? Any comments? It's your chance to, if you don't understand it, please ask. Okay, I'll do my best to answer the questions, but because it's important, the clock tree is very important. These are concepts that you must understand, so that if something go wrong in your design, where you don't meet your clock skew or your delay and things like that, you know how to debug it. Okay, so this is not a push button, meaning that you push and it runs and then they come out great. It's not going to be like that in the real world.
Hey, but I want to comment that I'm not sure in previous session you mentioned about difference between the generator clock, and let's say right here, right in this picture, you define a generator clock divided by 2 versus you define another clock at that same point, right? The difference is that during clock tree synthesis, the difference is that the clock tree from the main from the source clock, the master clock, it's going to traverse through the generator clock, right? So the same domain, right? But if you define another clock at that point, at the divide by 2, then the master clock going to stop right there, right? So it's whenever you define a new clock, it's very much terminate the previous clock, right? So I think that's very important.
Yeah, that was covered in the last session. So
okay.
if yeah, it's remember the stop pin, if that's the stop pin, if it's going to stop automatically if it's a source of another clock, which is this guy, right? So if you go back, and then this, if you don't define here, so what happened here is, remember, this is automatic recognized as a non-stop pin for ICG cell, right? I mean, the ICG cell plus the generator clock. Those is one of the 2 things that we talk about, the non-stop pin. Yeah, automatic traverse through here and through here if you don't define a generator clock. But if you define it, it will stop here because this is become a source of another clock, right? That was part of the, if you recall, the definition of a stop pin and not stop pin. So thanks, Tim. Yeah, it was covered in the last lecture.
Okay. All right.
Yeah.
Thanks.
Yeah, appreciate you brought that up. Sure. Okay, students, any question? If you don't have any question, I assume that you understood the concept, and I would just move on to the next topic. Okay. All right, so this is another important concept here I added here is buffer versus inverter-based clock tree. Remember, we talked about you can have buffers or inverters in using to build your clock trees, right? So what are the advantages and disadvantage, right? So what's the difference? So first, let's talk about the buffer-based clock tree. So a buffer basically is, if you look at it internally, a buffer is basically two inverters, okay? But for our clock tree buffers, it's actually built slightly different, right? Remember, it's a special type of buffers where we try to equalize the rise and the falls to maintain the duty cycle. Okay, so internal to the clock buffers, it looks something like this, okay? So the first one is relatively small, and the second buffer is high strength because it's got to drive much higher load out here. Okay, so this is internal. So you can see, okay, a small and a big, how can it have a equal rise and fall, right? So it's a little bit more challenging with the buffer tree. So in order to have an equal pulse width for high and low, okay, the RC delay seen by the first buffer, okay, must be equal to RC delay seen by the second buffers. That's how it's going to be equal rise and fall. So in the real world, you have a lot of things happen, right? You got OCV and things like that. So you're going to have some uh, unequal rise and fall, even with the buffers. Okay, so the buffer trees, there is the clock tree that use buffers, they tend to use a lot more power. Okay, more high consumption. High power consumption also is compared to the inverters, and then it's also more sensitive LCV. Anybody understand why it's going to consume more power versus just inverter tree? Take a guess. Just chime in your chat. I want to hear why the buffer tree is has higher, well, consume more power than the inverters. Think about we previously discussed, right? What causes power consumption, high power consumption in the clock tree. Okay. So go test it because buffer have high output capacitance. Not quite. That's the capacity here depend on the loading, the the length of the wires and width of the wire, right? That's going to be the loading on cap. Anybody else? Yeah, this is a little bit more difficult. Okay, so basically, um, when you build a tree, the equivalent, we assume everything equivalent, right? So there's going to be, it usually take less inverters to build a tree versus the buffers. Okay, so the buffer has two, so usually there are more number of buffers versus inverters on the tree. So basically, you're using more buffers to build the same tree versus inverters. So there's more buffers. Thus, it's gonna from that standpoint, you're gonna use more power. Okay. So sensitive to OCV. Okay, remember what OCV is? On-chip variations. Okay. The reason this is because there's more uh cells on the clock buffer. You use if you use the if you use a buffer tree, there's more buffers going, more buffer verse there. So there's more path you have to traverse through. So the more paths traverse through, the more chance the OCV is going to impact. Okay. So more areas because it's going to take more buffers to build a tree versus the inverters. This is assuming the same tree, okay? Same equivalent tree. It's going to take less inverter to build. Okay, so everyone understood this bullet here to have equal rise and fall poles. The RC observed by the first and the second must be equal. Okay, because you have the rise go to here and fall drop go to here. So in order to maintain these has to be the same loading so that it maintain the transition. Okay, so that's the condition for the buffers. You'll see the inverters on the next slide. It would not have that type of condition. Okay, any questions, any comments, any inputs from my colleagues?
Um, yeah, on the OCV, but you you mentioned about sensitive to OCV with the buffer tree because more likely you're gonna have a longer tree. Is that right? You
That's
have
right,
many,
because yeah, as long as
so
tree is go through a lot more paths, right?
right. And then if you look at the formula for OCV, it's stage based, right? So if you have a longer tree, then more likely the OCV going to be higher because of the stage, right? So it's the diversion, right? So the deeper the tree you go, the higher OCV. So
Yeah, you actually think we haven't talked about advanced OCV and advanced OCV is stage based, depth based. We just talk about the basic OCV.
oh, just the oh, I
Just
see,
OCV, yeah, that's advanced OCV is not a topic of this class. That's stage based, but the students look it up.
I see.
Yep.
Okay.
Yeah. So just want to introduce them to understand some of the there's a lot of there's a lot of thing if you dig deep down in. That's for more advanced class, PD class. This is just the fundamental class. So want to cover as much as we could on the fundamentals so they understand what OCV is, basic OCVs and so on. Yep. But yeah, basically that's what it comes down to is you get more. Do you think there's more logic? Okay, more paths, so there's more chance of OCV, more items, more nets, more cells that go through. So the more chance OCV impact, therefore it's going to impact your skew also. Okay, let's no question, students. Okay, well let's move to the okay, so can you say again why buffer tree is more power than inverter? So yeah, hi, can you so basically it for the same tree, it's gonna take more buffers to build the same tree versus inverters. Okay. So so basically by the nature of there's more buffers on the clock nets because the clock nets switch most often in your design. So you have more buffers on the clock net versus inverters, then it's going to use more power, right? So basically, it's more cells. Yeah. Okay, so now inverter-based clock tree. Okay, so just basically invert space equally. So with the inverter-based clock tree, it maintained the do-that cycle much better because why? You have one rises and then one inverter, rise inverter, equally spacing. So it just basically inverter phase back. So there's less chance of um, the duty cycle being distorted as compared to buffers. Okay. So everything's opposite. Better OCV tolerance because there's less stage, less number of cells. Okay, a low power consumption compared to buffers because there's going to be less buffers, also less area. So basically everything's opposite, better than the buffer built, right? So you can see this how it better maintain the poles, right? You get one invert equally back and forth. I had an example in one of the slide in terms of I think it was maybe the last lecture or one before where we had the duty cycle, right? And min pulse width, remember how it impact and then how it's better to fix it. So if we use this inverter based buffer tree, there's less chance of min pulse width violations, minimum pulse width. Okay, so yeah, so in the lab, we build the buffer trees. We didn't specify which one to use, so by default, we give both the inverter and the buffers. But in Innovus, there's a switch called set auto use inverter. If it's auto, it's always going to use buffer tree. So if you might want to change that to inverters, then it'll use inverter tree. You can play with it. Tell it just to use the trees only. I mean, use the buffer only, and then use the inverter onlys, and you'll see the number of inverters versus the number of buffers it added. Inverters should be a lot less. Should be less. Okay. Um, okay, so Ngô Thái Anh Hảo say, can you talk again why we need to use why wait, let me go back. Can you talk again why we need to use higher and lower drive string inverters to make a buffer, sir? Okay. So let's go back. Okay, so this is this you don't have to make this. This is how the clock buffers internally is built. Okay. This is the cell designer, they built this already. So internally, this just show internally, you don't have to build this structure. This structure is internal to clock buffer that you use. I'm showing here what it looked like internally because internally it has to use a lower string and then higher drive. Okay, so that way it can. This is a low string because really the wire delay here is really small. Okay, so very small load. So really the delay through here is a function of this input caps only. But here we need a larger buffer because this is the outside world. You could have a long net with then that's a higher loading, right? It's a C load, your capacitance and so on. So it could have a higher loading. So that's why we need a bigger buffers here. Okay, but this is internal to the buffer that you use. It's not something that you need to build. Okay, so when you use a buffer, this is what it look like internally. Okay, so it's not something that you're going to build, but this is just to show you what it looked like internally because in order for it to maintain best the rise and fall, this is where it's built. Okay, so hopefully that answer your questions. No time how. Okay, so there's okay. Nguyễn Lehman asks, does inverter-based clock tree is better than the buffer-based clock tree that we need to prioritize inverter-based clock tree in most cases? Yeah. So usually, it's better to build inverter-based clock trees than it is for the buffers. Okay, because of the fact that it's use less power, right? It's less sensitive, especially when you go down to a lower geometry, like less than 10 nanometers. You're gonna need basically transistors getting small, a lot things small. It's more sensitive to OCV and noise. So yeah, so it's preferred to build an inverter clock tree versus the buffer clock tree. Okay, so okay, all right, let's go. Okay, so any further questions before we change topic? Buffer versus inverter base clock trees?
Um, I think one thing I want to mention is that when you use the inverter, then this has to go in pair, right? So the number of stages has to be even, right? So is that going to affect your skew, right? Because in the buffer you can have, odd or even number of buffer, but in the case of the inverted tree, it has to be even number, right? So very much you have a less of the granularity, right? So you have to like 2, 6, 8, 10, you know, inverter instead of you can go like 7 and then 5 and then 3.
Yeah, good point, Hank. Students, do you understand what instructor Ting trying to tell you? So remember, a buffer is two inverters. So if you use this must be impaired because you can't invert your clock, right? If your clock needs to be positive at certain excuse me, and you need to get there, and if you have a odd number of flops, you just inverted your clock. Okay. So it always use pair, but the tool should be able to understand that. That's why you put it you in the set CTS buffers inverters. You give it both type, okay, and you put inverters as preference. But if you know that your clocks, you know your structure well, then you want to hand build on inverter tree, then it's yeah, then you can. Okay. But you need to understand the impact of the rise and fall of the edges whenever not to invert the logic the clock edge when especially when you driving a going to a positive edge flip flop and the last stage you missing inverter and it is falling then you just skip a half a cycle and that flop may not latch the data you need. Okay, think we spend time on this slide. Let's go to okay. So CTS optimization techniques, right? So this is the same for meeting timing in terms of setup and hold. These are the same techniques that we use optimization in placement, right? You should be familiar with all these techniques here. Bufferings, right? So cell sizing, resizing, different size, cloning, right? Splitting up, clone, BT swapping, and logic restructuring. So these are all the same technique in terms of fixing timing. Okay, so these are the same techniques that we're using placement for fixing timing. Same thing is going to be used in CTS. Same thing going to be using during routes. Okay, but less so because the timings uh, is 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 getting closer to being meet. So okay, so these I'm not going to talk about it. I'm just highlighted here. You should be familiar with by now. If not, you can restudy on your own. Okay, so these are the new techniques here I'm going to talk about is first one is cell relocation. So this technique is used during the clock tree balancing. Okay, so which means when I say clock tree balancing, it means minimize clock skew, minimize insertion delay. Okay, so when you balance the load, you're trying to balance the insertion delay to match delay all across the different branches of the clock tree so that you can minimize the skew, right? So when you minimize insertion delay, you're gonna reduce the power, okay? So what is cell relocation? It's moving or adjusting location of cells to balance the output load, reduce skew, and insertion delay. So here in this example here, this is before the CTO mean clock tree synthesis optimization. Okay, that's what it means. CTO clock tree optimization. So this is before. Okay, so for some reason the tools think that okay, I need to balance the load better here by moving this guy back. So physically in the uh, floor plan in the placement is going to move it further back to the driver here so that there's more loading in here so it can balance can match load across L2. Okay, so that's what it means by cell relocation. Relocation means moving to somewhere else. Okay, moving to another location. So it does that. Okay, so it sees that could be balance output, could be reducing skews, could be reducing insertion delay. So this is one of the technique it used during clock tree balancing. Cool. So this is pretty straightforward, right? I mean, just moving the cell so this cell can see more load here to balance off with these branches. Okay, so the tool does it automatically. The clock tree tool does. Okay, use various techniques as needed. It's not something that you specify or anything like that. So, but if something happened during CTS, you look at the log files or things happen, and you say, "Oh, why does this thing move the cell?" And you know why, because it's part of the CTS op techniques. Okay, so knowing these things will help you debug your clock trees. Any questions so far? Yeah, this can happen throughout different different trees. Okay. Okay. Next one that CTS does is called level adjustment. Okay, so this is a little bit different. So this is moving, adjusting sinks. Remember what sinks are? Which is like clock pins of the flops, right? To balance out the sync. Clock tree sync, which is the endpoint. Sync endpoint of flip-flops means sinks. Okay. So adjusting the level clock pin to higher or lower part of clock hierarchy. So this is one hierarchy, this is another hierarchy, right? So this is before CTS or CTO. Okay, and after it does level adjustment, it move it downstream, move it further down the tree. It split it up here, 1, 2, 3. Okay, so it does that because it sees that, okay, I need to balance delay here, delay here, delay here. Then, okay, before it doesn't, after, then so it does that by moving. That's what I mean by moving by level adjustment. So by moving the flops up or down the hierarchy. This is down the hierarchy. Good. This is the last part. This is the leaves. One called the leaves, the endpoints of the leaves of the tree. Okay, so level adjustment means moving the flops up and down the hierarchy to better balance the tree. So what happened is in the initial round of CTS, right? They put it here, but then initially, but then after everything's in, you can see, oh, I can go and fine tune this. So this is a kind of like fine tune step. It's I can move it here to achieve better skew, better insertion delay. That's the reason it does it. Questions or comments from it? So again, this is for balancing. These are techniques for balancing the clock trees, okay? Not for timing, not for fixing timing. Fixing timing, you already know. Okay. Okay, next one is called reconfigurations. Is reconfig meaning arrange it differently. Okay, when you heard the word reconfig, I mean arrange it differently. So reconfig flip-flops to further balance the loading. Or okay. So when you balance loading, you pretty much balance the delay, right? So trying to balance the delay in term minimize the skew. So reconfig here, this is before CTS. Okay, you see 1, 2, these purple flops on this branch, and after reconfig, it got moved, merged in with this particular branch. So reconfig merge moving. So this is a technique it referred as a reconfig. So notice it's not moving from level up and down because that level adjustment, right? This is just moving across the leaf same hierarchy. So it's just reconfig.
Bob, we have a question. Is there any type flip-flop we need to notice that is special case in level adjustment and reconfiguration?
Is there any flip-flop type of flip-flop we need to notice? It is especially in level adjustment configuration. So the tool does this automatically. Okay. All the I mean the tool sees the different loading. So depends on even this is like for this guy, right? It may not depend on the loading on this guy, the distance between the drivers versus the sink. So depend on that distance and the loading on this guy and it sees, and it will balance according to the timing requirement. So the timing requirement here being clock skew, right? So it's really not looking at a particular type of flops, other than just the loading on the drive on these branches here to make sure that when it move it, it will balance because it knows the caps on this guy and the loading, the distance on this, on the buffer driver, on the drivers. And then it will, based on that, it say, okay, if I put it here, then it balance. That's why I decided to go here. So the tool go through its algorithm internally to figure that out. So it's not really a particular type of flops. I mean, particular flop, I guess from the standpoint that positive edge and negative edge flops, right? Okay. So from that standpoint, it needs to, from that standpoint, yes, it has to match the edge, but you can't take a positive edge flop and put on a negative edge type of trees to make sure. Okay. So the only thing, yeah, I mean, the tool will know it doesn't mix the negative positive edge on different tree that will cause function issue, right? So it doesn't do that, but it will pay attention to those things. But in terms of this balance and loading, we can fix it just mostly just the delay, right? Loading. So ladies and gentlemen, say, could this config lead to congestions? Yes, it can lead to congestion. So the tool, there are times it can lead to congestion, but the good thing is, remember when this is done during clock tree, and the clock tree will be routed first. So before any signal routing happen, okay? So it could lead to congestion, yes. But the tool will first trying to meet the CTS constraint. That's the first priority it's going to meet. So yes, it could lead to congestion. That's why after each stage, we want to make sure that they are the congestion is still controllable, right? If after placing you have congestion, you got to go back. After CTS, you have congestion, you got an issue. Also, you got to go figure it out how to resolve that congestion. Yes, this could lead to congestion, but I hardly, in my experience, I haven't seen this particular type. I can recall that actually cause congestion where I cannot move on, I cannot proceed to the next stage. It may do additional congestion, but congestion, yes. Good point, ladies and gentlemen. Okay. Any more questions or comments? Okay, I will move to the next slide. Okay, so the next technique used is called dummy load insertion. So insertion means added into it, right? Something being insert is added to the design. Okay, so dummy means it's not real, right? Anything dummy is not real. It's not a real load. It's a dummy load. Okay, it's something you add in. So what is dummy load insertion? It is adding a dummy load on the different branches of a clock tree to balance their loadings. So usually it's added to the shortest path, right? So the shortest path, meaning it's fast. So we want to add extra loading to slow it down so that can match other tree. For example, here, this is before this being the fastest path, right? So there's I mean, the first thing is if this is the shortest path, we want to redo this here to match this guy, right? But this is two, may not, if the tool can't do this, can't not redo this two to match this. What it does is it's going to add a dummy load here to slow this guy down to match the insertion delay of these two guys. Okay, and that is when it uses insertion the dummy load insertion. So the first choice is actually redo this insertion, but it cannot, then it'll add a dummy load here. Okay, so there are three types of dummy loads. Okay, it's called, the first one, if you're using a buffers, it's called buffer-based dummy cell or dummy load, right? And then this example is a buffer. The other one is an inverter, right? It's the end of the chain. It doesn't really matter, it's just a loading. And then the other was RC base. Can anybody tell me what RC base dummy loading is? How can you get an RC base dummy loading? What does that mean? So you know what a buffer is, what inverted, what is RC base? How do you do that? You can verbally speak or you can chime in the chat. I purposely not adding elaborate here. I want to see if you guys can think and see what RC base mean. Ngô Thanh Hảo say handling wires. That is correct. So what you do is here, instead of add buffer, you just add wire antenna, wire going different directions, right? Up here, sideways, whichever you have tracks for. That is the RC base. So basically, you're adding capacitance loading onto this to slow down this net. Great, no Tanhao. Yeah, that's what RC loading means. Is you add wire instead of buffers or inverter. You add just wires to load down this buffer, so to slow down this particular branches. Okay, great. Any questions on dummy load insertions? Why we're doing it? Why the tool's doing it? So, by understanding this, if you look at your design and you see when you debug it, usually when you have issues when you start debugging, you say, okay, why this tool have these buffers on this here? It's not part of my design originally. Why the tool added in here? Understanding this, that the technique dummy load insertion, oh yeah, the tool use dummy load insertion is actually added in there. Okay, if it screws things up, you can go delete it. It still doesn't impact your function on your design, right? If you don't understand this and you have no clue what happened here, then you might be in a difficult time to debug, try to figure things out. So the woman asks, so the tool will help us with the selection of dummy type and the insertion, or we will have to choose ourselves. So yeah, so before you do it, so each tool will have its default, right? Some tool have default as buffers, inverters. Okay, you set it up front. You configure up front. Is if you don't do anything, and they'll use the default buffer or inverters. Okay, I believe Innovus, I believe it's buffers. Okay, so you set it up front. If you don't set it, the tool will have a default. Default means it's automatic setting that it's going to use. Okay, so you can get you can query the setting. So we got to figure out. I forgot what the setting is, but you can do a get db and something about dummies loading, and then it'll come back to tell you whether it's inverter buffers or RC. Okay, and if you want to change it, you can change it. So yeah, it's a lot of these setup is default, and then you can change, you can configure what you want. Okay, so hopefully that answers your question, Min.
But I think I want to add that understand these technique is very important when you do ECO. So because when you do ECO, you have limited, flexibility, right? So by understanding these techniques, sometimes you can just say, well, how I'm gonna fix the whole time, right? So you can connect, one of the load to a spare cell, right? And then understanding the technique here, then very much you can slow down the clock branch that connect to that spare cell, right? So most of the time the tool does it for you, but understanding the technique is very important, later on, especially during ECO. So
Yeah. So yeah, the student, you remember what ECO mean? Engineering change order. When you can have functional ECO, you can have timing ECO, right? So remember we have pre-silicon and post-silicons, right? So ECO cycle, basically toward the end of the design, we have a very minimal, like minor timing fixes. We can do each timing ECO, meaning fixing like once the design's already routed and everything, and it's gone through a lot of fixes, a lot of things have been added, dummy metals and everything. And we want to do a timing fixes or timing ECO. We want to minimize the changes on the design, right? So it'll be quicker, be much quicker. For example, if you want to fix hold time, remember what hold time is? Hold time is the data has to hold after the clock edge, right? Meaning it's on a min delay check, right? So to fix hold time, usually you want to, lengthen the load on that flops. Okay, so a lot of time what we do is we just do an RC base. We just add wires to that flops that has hold time issue. Okay. So we just add RC instead of adding buffers or anything. We just add wires to it. So it will slow it down. If it's barely, let's say missing a couple picosecond, and we figure, okay, the wire this wide and going this long micron, it should be enough slow down for this 2 picosecond. So that's understanding this will help you quite a bit later on in your job. Good point, Dan. Thank you. Okay, so okay, so yeah, okay, dumb insertion. Okay, can you say this is what if technique or actual insert or actually insert the spare cell? Okay, so this is not considered spare cells. Spare cells is different. Okay, spare cells are there for you for future ECO. I think you got confused a little bit when we talk about ECO. So spare cell is added in there for future ECO. This is the actual technique this is called dummy. Okay, dummy. So it's actually when you spare cell, you insert it there. Hopefully you use it next time, but not now. Dummy load insertion. These are the cell you use it right away to fix your CTS timing. Okay, as a dummy load to balance out these branches, your insertion leg with the rest of them. So this is actually being used. So it does not refer to a spare cell. Okay, spare mean something you insert for future use for backup. That's called spare cell. Okay, so let's be clear on the spare cell and dummy load insertion. So this dummy, the reason you insert it because you need to use it right. You need to connect it right away to slow down the delay, the shortest path, the fastest path to balance your clock tree. Okay, or any other timing issue you have. Okay, you can manually do this on your signal you want. Okay, but the clock tree will use this, the CTS tool will use this technique to balance the clock tree. Okay. So the spare cell is completely different concept than dummy level insertion. Okay, so spare is inserted for future use, for ECO use. Dummy cells is inserted right away, used right away, make connection to slow down the fastest path. Okay, shortest delay path, fastest delay path, same thing. Okay, so hopefully that you understand the difference between spare cell and dummy load. Okay, so let's do one more. Okay, load splitting. I don't think we talk about load splitting. Okay, splitting in English means splitting means divide something in half. You split something in half. You split something in four, third, fourth. So basically chop it in half or split in half. So it's a process inserting buffers to split the fan outs and resize the current drive to meet CTS or DRV constraints. So this technique is used in CTS, also in DRVs, right? So there are two types of load splitting. So you can see here a buffer A is driving 4 buffers B's here, okay? So let's say there's too much load on buffer A. We want to split this load, right? Split it, meaning cut in half. So one method for load splitting is called cloning, and you know what cloning is, right? To clone the logic. So basically it clone 2 buffer A's here and split the load. So clone A, buffer A, and then driving 2 loads. So split the 2 load become 1 load. 2 load become driven by A1 and 2 load become A2, right? So it's load splitting via cloning, meaning you cloning to split the load. Okay. The second method of load splitting is buffering, right? So basically combine the two. It put a buffer there, buffer in it, right? So and a buffer here. So it's just buffer it up. 1, 2, 3. So that is the 2 method of load splitting that's available to the tool. Okay. So any of these techniques the tools use, you can manually fix. You can manually use. So understanding the impact and how to use it, what's happening, you can go and fix timing or fix DOV by doing this. If the tool can't do it. The reason you come in and touch it is if the tool can't do it, or at the very end you design you don't want the tool to touch it or mess things up. About to tape out meaning you are almost done, send it off. You want to minimize changes as much as possible because your timings are in place. You want to minimize impact. So you understand is you can actually do it's like a doctor doing surgery on your chip. When you change a little bit only to fix what you need and not let the tool touch it. Okay, so at the beginning, when you do it, you let the tool touch, going through CTS, going through placement, going through routing, going through optimization, but toward the end, when you have all these other things in, all these other, all your routings and all your fields and all your time fixes in, but if you have specific path that has to be fixed and the tool can't fix it, you go and then you can fix it yourself by understanding these techniques and manually fix it. Okay, why don't we, any questions here? So this is it's come to the end of the CTS optimization techniques. As far as the next topic. So why don't we take what time is it now? It's a good time to stop. Why don't we come back at what time is the day? I don't have the time right now.
It is 1 minute till 10 o'clock, so 9:59.
Okay, we'll take about 6 minutes break real quick, and then we'll
Okay.
come back.